Hey, what's up, guys? This is Sheng here. So today let's take a look at number 424, longest repeating character replacement. I think this is a pretty interesting problem. Okay, you're given like a string S and it consists of only uppercase English letters from A to Z, and you can perform at most K operations on that string. So for each operations, you can change any character to other characters. And you need to find the longest substring containing all the same letters you can get after performing the above operations, right? And the some just you can there's a note here will not exceed 10 to the power of 4, right? So which means that I think it's expecting you to either come up with an n log n solution or like the or O(n) solution, right? So a few examples here, right? Basically, we have A, B, A, B, right? So here we have k equals to 2, which means that if we can either change this 2b to A or change this 2A to B. And another example here, right? So we have this AA, BA, BBA, and we can only change one letter to a different one. So in this case, we need to change this this B here. We need to change this B to A so that the maximum length we can get is 4A's. Okay. So so whenever we see a maximum length for a string, right? For a string problem, I think first thing come to my mind would be something like, actually I was thinking of DP at the beginning because I know DP can certainly give us some maximum length, and there are like other like string related DP problem that can give us the longest length of the string, like the longest increasing subsequences, right? Something like that. So and one so basically one of the candidates DP. What's the other one? The other one is like greedy, right? Greedy can also give us the longest, right? And then the third one is what? Is the sliding window. Sliding window can also give us the either the minimum or the maximum result. So I think first thing I abandoned was the greedy, because obviously there's no such greedy approach here, because depending on the relative positions and what's before this current one and what's after the current one. So there's no clear greedy approach for this problem. So I just abandon the greedy one. And then between the DP and the sliding window, I thought about sliding window at the beginning, but I didn't find a very straightforward solution for sliding window, because I was thinking about, so once we increase, we get a new, we're at the new letters, we can count the numbers, and then when we are removing the letter out of the sliding windows, we need to decrease the count. But after that, I think I had a feeling that I need to do something else, but I just couldn't figure that out very quickly. That's why I think I spent some time trying to figure out if the DP can solve this problem. Basically, I was trying to use like the DP I and K here. I was thinking that, can I use like 2D DP here? Basically, the I means that, um, from 0 to I, and with K operations, the longest repeating characters, to delete the longest repeating character string. Mm. But then I realized that, I spent some time trying to implement this, but that I just realized that, and the whenever we're reaching let's say when we reach the A here, A B B here, and let's say we follow one pattern, which means that, if the current one is different from the previous one, we just change this current one B to A, right? But that's not always the case for DP, because later on, when we have like, you know, we have B, 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 A, and B. In this case, we need to change A to B, not the B to A, right? So which means that, the later state will affect the previously's decision. So that's why I I couldn't figure out the DP solutions. Basically I had to stop in that route. So and then I came back to the sliding windows, trying to figure out the sliding window logic. Basically, we already talked about a little bit, because for basically, whenever we have a sliding windows, whenever we're including a new letter to a sliding window, we will increase the count for the letters in the sliding window. And whenever we're removing the letter out of sliding window, we decrease the count. Okay. And okay, so now we have a valid sliding window, and then what's to do next, right? So within the sliding window, right, it says we need to maintain, basically, we need to make sure the sliding window has can be this sliding window can be changed to the repeating characters within k operations, right? So basically that's gonna be our goal of doing that. But how can we make sure the letters in the sliding window can be changed to the to all the same letters within k operations? So we have to basically we use a like kind of greedy approach here. We have a count, right? We already have a counter, an updated counter for the current sliding window, right? And how can we okay, we have in basically, we have include the right letters into the counters, and then now we're trying to shrink the left pointer. So then what's going to be the rule of shrinking the left window? Basically, we keep shrinking it. We shrink it when the sliding window cannot become all this to become all the repeating characters within k operations. And how can we verify that? Of course, the strategy will be we get the maximum count. We get the maximum count from the counters for all the strings within the sliding windows. And because, and the maximum count will be our base. Basically, the max count will be the repeating characters. And what's remaining, then total minus max will be the operations we need, so that we can make this sliding window string to be the repeating character for one letter for one character, right? So this is pretty obvious, right? Because we just pick the maximum letters as a base, because so that the total minus max will so that we need the least operations to change all the others, and we keep doing it until this total minus max is either smaller or equal to the k. Then we know, okay, that sliding window is the sliding window. It's a valid sliding window, and we can update our answer. Yeah, so and that's basically the a little tricky part to maintain the sliding window. And with that being said, I think we can start coding here. So we have a right, and let's see, we have a let's do it let's do n here, and it's equal to length of s here, and then we need a counter, right? So the counter will be the default dict of int, right? And then we have a answer equals to 0, since we're getting the maximum, the longest, right? And for sliding windows, the right pointer is in the while loop, right? In range n here. So first, like I said, we're gonna update the counters, right, by the current characters, which is gonna be the s dot right? We do this +1, right? And then we try to maintain this shrink this sliding window so that it can satisfy the conditions here. So the conditions we're having here is, so what's the total? What's gonna be the total length for the current sliding window, right? So the total length is what right minus left minus one +1. Sorry, right? This is the total length of the current sliding window. And if this one is and minus, right, minus the maximum of what? Of current counter. So counter is like the value of the counters, right? Because since we're using like dictionary, so I only need the maximum count. So that's why I'm using counter dot values. And this thing will give me a list of all the values in this dictionary. So I subtract these things from this count list, the maximum. And if this one is greater than k, right? So it means that with this length and this maximum count, we cannot make this sliding window by we cannot make the sliding window valid by making k operations. That's why we have to shrink the left pointers. So after shrinking the left pointers, we need to update the left the counters by removing the left characters from the counters, and then we also need to do a left +1, right? Because after these things here, right? After removing this one, the value of here it might change because after removing this one, the other letter might become the maximum might become the letter that has the most appearances, right? And when this while loop is finished, now we have a valid sliding window. We can just update the answer equals the maximum of answer dot right minus left +1. Okay, and then we return the answer. Yep. So run the code. So this one works and submit. All right, so success. Yeah, and for the time complexity, right, as you guys can see here, we only have like a while loop, for the sliding window. I mean so we have ON here, right? We have ON here. So I mean, it seems like we have like a maximum here. It seems like we have another layer of the of ON, but remember remember the problem tells us there the string s only consists of only up 26 uppercase English letters. So at most, so the counter size at most is 26, right? That's why we're considering this max of 26 element is O1, right? That's why the total time complexity is still O of n, right? And space time complexity is O1 because the size of the counter is also limited to 26, right? So that's the space. This is the time. Yeah. Yeah, I think that's it. I mean, just to recap, right? I think this is a interesting sliding window problem because this is not the traditional one because it needs us to dynamically calculate the current maximum frequency within the sliding windows, and then we need to use that one to check the validity, if the current validity of the sliding windows. And after that, it's just like the template of sliding window. Cool. I think I'll just stop here, and I hope you guys like this video. And thank you so much for watching it, and stay tuned. I'll see you guys soon. Bye bye.